Welcome to week 1 of Boltzmann Law, Physics to Computing. This is the 5th and last lecture for this week. Now, what we have been doing this week so far has been to try to summarize the key concepts of equilibrium statistical mechanics, like the Boltzmann Law, the concept of entropy, and free energy. Now, what we'll be doing in this lecture is somewhat different. What we'll be talking about is what you might call a practical approach to describing large interacting systems. So what we have seen is that this Boltzmann law describes this equilibrium condition, and this is a very general law, applies to any system. But one thing about it is that if there are these n 1 electron levels, then there's 2 to the power n states. Now, what that means is as n increases, this 2 to the power n actually increases very rapidly. That's like exponentially. And just to appreciate this point, I've put together a little table here. N is 1, well, 2 to the n is 2. If n is 10, 2 to the n is about 1000. Now from 10 to 20, point is 1000 becomes like a million because it gets squared, it being in the exponent. Going to from 20 to 40, that gets squared. And so it becomes enormous, like in a hurry. And so once you have a reasonable number of states, this working in state space, although conceptually very sound, but in a practical sense is often very difficult. So what I'll be describing to you is a method that is widely used all over this general condensed matter physics, semiconductors. Everywhere we are always using this method to describe electron-electron interactions in general. And this is the method that we'll also develop further next week when we go into neural networks, for example. Now, but the key point to appreciate is that there are these two types of space, like the n space and the 2 to the n space. And the 2 to the n kind of gets unwieldy in a hurry. Okay. Now, so to understand this practical approach then, let's start from what we have been describing so far, that you've got a bunch of 1 electron levels. Each level can be occupied or unoccupied. And so in the state space, you have states that are described by these binary numbers like 1, 0, 0, 1, etc. Now, if you have, say, 10 states, then there will be 1024 states in state space. So these 10 states have different energies, which I have shown here. And I'm assuming that this electrochemical potential is at 0, right around here. And these are these 10 states. And what we'd like to know is, what is the occupation of these states? How are they occupied? Now, Boltzmann law tells us how they are occupied at equilibrium. But the thing is, the Boltzmann law applies to the state space, which is not the n equals 10 space, but rather the 2 to the 10 space. Okay. So the way you would apply the Boltzmann law is to say that, okay, let's consider a particular state, say 1, 0, 0, 1, 0, 0, 0, 1, 1, 0. And we want to know its probability. So to apply the Boltzmann law, I first need to know the energy and the number of electrons involved in that state. Now the number of electrons is the number of ones, which is 4. What is the energy? Well, all of these are empty except for those 4. So the total energy is epsilon 1, that's the energy of the first one, and then the 4th one, and then the 8th one, and then the 9th one. So epsilon 1 plus epsilon 4 plus epsilon 8 plus epsilon 9. Okay. Now what you could do then is write down the probabilities of all these types. So this one has a certain probability from Boltzmann law. next one has a certain probability, and then you add up the probabilities of all the 512 states that have r equals 1. So supposing I want to know, well, what is the occupation of the fourth state? Well, when I write down all of these 1024 states, half of them will have 1 in the fourth state and half of them will have 0. So what you do is to consider the half that have 1, add up their probabilities, and that will then tell you how many electrons are there in the fourth state. So that's how you could do this if you are starting from the Boltzmann law. Of course, it forces you to work in the 2 to the 10 space. But in this case though, if you just applied the Fermi function to each one, so now each one you look at these 10 levels and you apply the Fermi function to this one, then you would have come up with exactly the same answer that you get from this much more elaborate procedure using the Boltzmann law. You can see I've compared the Boltzmann law to the Fermi function. They match each other perfectly. And the Fermi function, of course, you can understand easily. You see, those levels that are above the equilibrium chemical potential, like this one, they are weakly occupied. That's why the Fermi function is relatively low. Whereas the ones that are way below the equilibrium chemical potential, that's where this is a negative quantity and the Fermi function is higher. It is more occupied. So in this case, you could do it either way and you'd get the same answer. And then you'd say, well, why am I even wasting my time on this 2 to the 10 thing? Let's just work with the 10 space. Okay. But the problem is that as soon as you include interactions, the answers you will actually get from Boltzmann law, that's these blue ones, are very different from the answer that you'd get if you just applied the Fermi function. You see, they don't match at all in this case. And we have assumed that there is some interaction energy in this case, and that's why they don't match. If it was completely non-interacting, then it would have matched. Now, how do you include the interactions? Well, in terms of Boltzmann law, the point is that when you evaluate the energies, you not only add up the energies of all these levels like I had done, but you also add the interaction energy. So what is this interaction energy? Well, let's say U is the interaction energy per pair of electrons. So the overall interaction energy will be U times the number of pairs, which is what I have written here, that you count how many pairs there are. So when you have 4 of them, then the number of pairs would be like 4 choose 2, because you see I've got 4 of them, and when I can take any 2 and think of it as a pair, right? So how many pairs are there? Well, it's 4 choose 2. In this case it will be 6, and you could write them out actually if you like. So you know the occupied levels are 1, 4, 8 and 9. So how many pairs are there? Well, it can be 1, 4, 1, 8, 1, 9, 4, 8, 4, 9 and 8, 9. Those are the pairs, and there are 6 of them. Okay, so the energy is 6U. So this way, when you're applying the Boltzmann law, you could actually take into account all these energies of this overall system, of these 2 to the 10 states, and then do what we had done before, and that's how you'd get this blue curve. And the point is, it wouldn't match the Fermi function at all. And this then leads us to the question that when I have an interacting system, how would we actually get the correct answers? You'd say, well, apply Boltzmann law. Yes, but then that requires us to work in this 2 to the 10 space. And as I mentioned at the outset, that's the quantity that, okay, 1000 is not too big, but if instead of 2 to the 10 we had 2 to the 20, it would be a million, and if it is like 2 to the 40, it would be like a trillion, right? So this is the number that goes up in a hurry. So we need a method for dealing with these interacting systems, a practical method, okay? And that's what we'll be describing. And now, and this is what's generally called the self-consistent field method. And as you realize, electrons are interacting objects. So in general, whenever you're dealing with any practical system, I mean any solid, anything that you want to calculate probabilities, you have to take into account these interactions. So how do they do it? And that's what this self-consistent field method is about. So the way they do it is, well, what would you do if there were no interactions? The idea is that, well, look at these energy levels, find this quantity, this dimensionless quantity, and then find the Fermi function. And as we have mentioned, this Fermi function looks something like this, which starts at 1 for negative x and becomes 0 for positive x. That's the Fermi function. Whereas it's kind of the mirror image of this sigmoidal function, sigmoid function, which goes the other way, right? So f of is equal to sigma, the sigmoid function of minus x. Okay. Now, the self-consistent field method kind of says that, well, these bare energy levels are these epsilons, but we define a interacting energy level, which we have put this tilde, and what the way you think is as if each of these energy levels gets raised by an amount of that depends on how many levels are filled, because you see every time there is another electron in some level q, it gives rise to an interaction energy with this rth level, and that interaction energy is u. So what you have to do is you have to add up these effects of all the occupied levels except for itself, because no electron affects itself, it just affects the others. Okay? So you calculate these new levels now, which include interactions, and then you apply the Fermi function. So these are the energy levels, and then if you like subtract mu and divide by kt, you get this dimensionless number x. And there also we have a tilde x, and the one that's corresponding to epsilon r, the x we had before. And we take the Fermi function of this in this tilde x, the one that includes the interaction. So that's the idea, that if you do this, then you see it is almost as simple as doing the non-interacting case, but not quite. It's actually a little more complicated. And the reason is this, that you see, when we didn't have this interaction term, it was straightforward. You calculate x, find the sigmoid or Fermi function, and you have your answer. Now you see I can't calculate x till I know f. So what I have to do is I assume some x and use it to calculate the f, but then I use that f to recalculate the x. And of course it won't match what I had started with. So what I do is I take it, feed it back again calculate an f, come back, and keep iterating till the result converges. So that's this called the self-consistent field method. So you do this till it get a self-consistent answer, and this is the method that is widely used everywhere in condensed matter physics and in device physics. Okay. Now this actually works quite well if the interaction isn't too large. So for example, I mentioned earlier that when u over kt is 1, I showed you results that the Boltzmann and the Fermi function were not matching at all. But once you do this self-consistent method, they match reasonably well. You'll notice it's not exact, and actually numerically if you check the difference between these two distributions, there's about a 7% difference. So it hasn't matched very well, and if u were bigger, actually the discrepancy would also get bigger. But for relatively small u, it works quite well and is, as I said, widely used in this field. Now if you plot these tilde x's, then you'll get these red levels, the ones I've shown here. And so you might ask then, well, in practice when people draw energy levels, which ones do they really mean? Do they mean the red ones or the black ones? Right? The levels that we normally draw. And the answer is that it's really the red ones that you are drawing. It's as if the interactions have already been considered. Now, how do we know that? Well, consider first how you actually measure these levels, these 1 electron energy levels that we commonly use. How do we measure them? The idea is that if you want to measure a level, you do what's called a photoemission experiment. You hit it with light, knock an electron out, and then see what photon energy is needed to do that. Now, what will be the photon energy? Well, the answer is the photon energy that we'll need will be the difference in the energy between this configuration and this configuration, where they are basically identical, except that in one case the rth level is filled, in the other case the rth level is empty. And that difference is what the photon energy will measure. And what is the difference? Well, that difference is really equal to this tilde. Why? Because what is the difference? Well, first term is epsilon r. Here there's an electron, here there isn't, so the energy difference you'd say would be this bare level. But then as soon as I take out the electron, I've also removed its interaction with all the other electrons, and that's this second term. So finally the photon energy that is needed is not just the bare level, but also includes the interaction term. Now another way to think about it is, well, what would you have expected from Boltzmann law? So what Boltzmann law says, that if you consider any two configurations like this one and this one, which are identical except that in one case one r is occupied, in the other case r is not occupied, then the probabilities is proportional to this e to the power minus E1 minus mu ni over kt. Okay? So the way we are doing this then, when probability nr equals 1, then it would be e to the power minus E1 minus mu n1 over kt, and probability that it's nr equals 0, that's this one, would be this. And we have kind of switched the minus to a plus and turned it around. Now, of course, the probability it's 1, that's what would be Fr. Probability it's 0, that would be 1 minus Fr. And when you look at this ratio, you see E1 minus E0, that's this tilde epsilon, that's the interacting energy level. And N1 minus N0, well, that's 1, because N1 is the number of electrons in one case, N0 is the number of electrons in the other case, and they basically differ by 1 electron. So N1 minus N0 is just 1. So you get this. Now, from this, just with a little algebra, you can show that Fr is equal to this relation, that this Fermi function relation, which is also the sigmoid function of the negative. Right? So Boltzmann law also kind of leads you to this same idea, that basically what you have is these interacting energy levels, and then you have to apply the Fermi function to the interacting levels. And so in general, what you have to do is you have this Fermi function, and then you have this self-consistent field, the self-consistent levels, I guess. And these two have to be solved together self-consistently. You have to iterate till you get a consistent answer. Now, one little thing is, I generally assume that this U, that is the interaction between the qth electron and the rth electron, is constant. In general, what could happen is you could have different interactions between them, because levels R and Q may be right next to each other, in which case the interaction would be large, or they could be far away, in which case it would be small. And so you can generalize it to put U R Q instead of just a constant U. And then the point is, these two equations, this 1 and 2, would have to be solved iteratively to get a self-consistent solution. And what I've drawn here is these two pictures, which are basically pictorial representations of those equations. Top one is the sigmoid function, and the bottom one is this summation. And the reason I'm drawing it this way is, of course, next week we'll be talking about neural networks, and in the context of neural networks, you often see these pictures, the kind of the sigmoid function and what you usually call the synapse. And we'll see how these self-consistent equations can be generalized, to describe neural networks, etc. But that's for next week. So summarizing then, I guess in this lecture, we introduced this practical approach for large interacting systems, which allows you to do these calculations in n space and get results that match the exact results from the 2 to the n space. And what we'll be doing next week then is going on to our next topic, which is about Boltzmann machines and neural networks. And those of you who are interested, I guess you would be taking this exam 1, you might want to look at the 5-minute summary of everything we did this week. Thank you.